So in the last year and this January, so AI has the potential. AI has taken quite a rapid development, I would say. For example, if you follow some technical blogs or some news in the AI site, you would be able to see ChatGPT has taken a quite a good sensation. So it is basically a text-to-text model. And apart from that, we have Delhi and Midjourney AI. If you give a text, it would be generating an image. So that is where AI now. But when it comes to healthcare, it is a bit of different because the decisions that you are taking from the healthcare model, machine learning model, would be really critical. It would be determined whether the person is going to die or is they're going to live. So before going to that one, I will briefly explain what is healthcare. So healthcare means basically improving patient health via prevention, diagnosis, treatment, or cure of disease. It can happen anywhere in the hospital, that from doctor, from nurse, like that. In home, that you when you are making some kind of tea when you are sick, so kind of it is also kind of a healthcare. And when PHI come to your home to inspect dengue or some kind of thing, or when the PCR test something, and those are also happening healthcare. And in schools, there are some vaccination program. It is also part of healthcare. So healthcare field is going is not limited to hospitals. It is widespread sector, I would say. Then, uh, what I also ask is, where can AI come to help? I would give an example. If you in past few years within the COVID-19 period, so doctors, healthcare professionals suffered a lot. For example, burnout because of the number of patients. So basically, uh, it can come from anywhere to help. AI can be used to healthcare is like analysis of medical data, because AI has capability to analyze large amount of data in quite a small time. So by using machine learning algorithms, so can quickly and accurately analyze those data and identify those tiny details, because doctors can is identify it, or because those burnout and seeing like thousand x-rays or data, it is really hard case. And then apart from that, also diagnosis case, like maybe analyzing medical images, x-rays and MRI, it can help. uh, sorry. So this can help doctors to make faster and more accurate diagnosis, which can lead early and more effective treatment for patients. So I will explain those things in bit of in next slides, like what are the current research as well. So I will mainly explain about what is medical imaging. So basically, it is a set of tools and techniques to image different organs. It is important for diagnosis, prognosis, and treatment. Also, some people call it as a radiological imaging. So in this session, there will be two words that I will be using. First one is diagnosis, other one is prognosis. Diagnosis means identifying name of the problem. Basically, doing detection of the disease, I would say. And if you watch some TV series like medical drama TV series, that you have seen like differential diagnosis. That means when more than one possibility for the diagnosis exists, for example, a chest pain. Uh, so it might be just a pain that you have, or it might be a symptom of heart attack. So these possibilities is need to determine the actual diagnosis and decide the treatment plan. It is one of the challenging problem, I would say, differential diagnosis. And then we have prognosis. It's basically predict the outcome of the treatment. For example, a patient diagnosis brain cancer, you give some treatment, or okay, then will patient will recover or not, like that. So I would go briefly into how medical images are acquired, because that is the data is the most important when it comes to AI in healthcare. So briefly explain, you may have known those things like X-ray, CT, MRI, ultrasound, PET scan. Apart from that, we have histology, that blood samples as well. So X-rays is I think everybody have taken X-ray in your life. So X-ray is basically it penetrate your body, but not bone. So based on the absorption, it will generate an image. So those shadows are recorded, and it is a 2D image. So X-ray is a bit of noisy because of the physical interactions, and the manufacturers aim to reduce the dose of X-ray because that it is a bit of harmful, and that might compromise the quality and main quality, and it will also add noises. So there are some research that going on how to improve the image quality in X-ray image using machine learning models. And there are some noises as well, and because of the patient movement, and we can use some filters to remove those as well. So in these X-ray images are a bit of high dimensional, and but we only relevant is only maybe small region. So histograms, autorecorders, wavelet features can be taken to use those capture those features. Uh, I want to show you one example. This is the first X-ray image that has taken in in the world. So I can't remember who the person developed this one, but as you can see, you can see his ring as well. And the next one, this is the full body X-ray, first full body X-ray image. It was taken in 1897. Uh, Next, I would move to how to use X-rays and ML. X-rays in machine learning. For if you are going for extract features, as I mentioned, you can use histograms, autoencoders, and wavelet. And as you know, deep learning has taken quite a development. So in this case, if you have classification, you can use VGG, ResNet, EfficientNet kind of algorithm, and detection for the detection task, YOLO, RCNN, and for the segmentation, UNet and DeepLab. I won't be going to in detail what is classification, detection, and segmentation tasks. I assume you have knowledge about that, but if you can Google those as well. And if you need some data set for X-ray, you can follow this site, Chexpert and NIH Chess X-ray. You can find different X-ray images in different areas in the body. So you can download those as well if you're interested. Next, we have CT, normally known as CT, but long the name is computed tomography. So basically, it is a 3D version of X-rays. So X-rays are fired from different angles, and detector captures those shadows. Main thing is there's a difference in X-rays and CT. In X-rays we have pixels, basically it's 2D. In here we have voxels because this is 3D. So in pixels we have only x-axis and y-axis. Here we have x, y, and z axis as well. Apart from that, this is a bit of a GIF image that how X-rays are taken, and this is how a 3D image will be look like. And there's one important thing that I want to mention. X-rays that is normally, if you know about the images, that you know it is going from pixels, that means 0 to 255. So classical natural images, also X-rays are going from that range. But CT images are not 8-bit. 8-bit means this is not going from 0 to 255. In most cases, CT data is expressed as sequence of 16-bit sign integer. That means it has negative values as well. So if you are processing CT images, you might have to look into how it is stored and what is the pixel range, and based on that you have to do some pre-processing to get the extract to get the you wanted range and remove the unwanted area. There are some algorithms that has developed for remove CT artifacts. Artifact means basically a noise. First one, we have strict artifact. Then we have partial volume. That is the main two common things in CT. CT in strict artifact means you can see there are kind of like white background here. That is known as strict artifact. You can use Fourier transform kind of algorithm to remove those artifact. And then we have partial volume. Partial volume happen in like low quality CT scans. So one voxel represent a large physical region. So then partial volume appears when voxel represent two or more different tissue types. It mainly happen in the boundary, as you can see here. So there are some algorithms to remove those as well. So if you are using CT images, you have to look in the image quality. So based on that, you have to apply those algorithms to remove those noises. Then we have MRI. MRI is a bit different compared to CT and X-ray. It has a powerful magnet. So when radio frequency current is then passed through your patient and the protons are stimulated. And when frequency turn off, MRI sensors are able to detect the energy released from those protons. It is very non-invasive 3D images, no radiation, that is the big advantage, but it's really expensive. Really expensive, and it's taking a long time, it's taking long time to take image. So apart from that, as I mentioned, this is a magnet. So if you have magnetic implants such as, let's say, artificial joints, pacemakers, you can't use it because it would be damage you and also the machine. So if you have taken MRI, so they are asking to remove any magnetic or even earrings as well. Then there are some another thing called fMRI, functional MRI. So it is basically used to blood flow in the specific brain areas to identify specific place. So basically, if person telling truth, your brain part will be highlighted. If you're lying, another part will be highlighted like that. So it will be able to highlight the blood flow in a specific area in the brain. So this is basically a MRI scanner. And as for the MRI artifacts, as I mentioned, it is taking a long time to take. So patient can't stay still. So patient is moving, and based on that, there will be what we call motion artifact. Then we have partial volume. It is the same thing as in the CT. Then we have aliasing and truncation. So aliasing means the field of view is smaller than the body part that been images. And truncation means, I think it's better if I show you with the image. So as you can see, this is the patient movement. Then we have aliasing. As you can see, there is a white line that is going here. That is called aliasing. Then we have truncation. Truncation is basically means this is a white line that is going from the around the brain image. So that is also known as Gibbs artifact as well. There are some algorithms and some research that is going on to develop how to remove those artifacts in general. Then we have ultrasound. It is a very simple machine and very simple mechanism. There is a machine that can emit ultrasound waves and detect the ultrasound echoes reflected back. So the sound waves are reflected to the transducer by boundaries between the tissues, and when the echoes hit the transducer, it generates electrical signal. Then it will be translated into the image. Basically, widely used in video analysis. And if you are pregnant, pregnant mothers are using that one to identify the fetus like that. So basically, it is basically like that. It is simple mechanism. And as you can see, as I mentioned, it is widely used to identify fetus as well. And apart from that, we have PET scan. It is basically we inject the radioactive substance into you, and then we follow the blood flow, and based on that, we are generating image. Uh, that is the basically image settings that we have in the hospital. Apart from that, we have histology as well. So this is what I want to show you. This is called EchoNet. It was developed by some researchers. Uh, I can't remember, but here uh, you can see how normal blood flow and low ejection fraction, and if there's arrhythmia, how to identify those. So this was helpful for to identify those regions and how those are ejection rate as well. Then I want to briefly discuss about how normal images and medical images are different. Because if you're going to Google, if you search some dog images or cat images, this what we call as natural images. But medical images, we are this bit of different. Normally, uh, it can be found in both RGB and grayscale, but most of the cases that images are grayscale. But if you go into MRI, CT, some of them are RGB as well. And when we have, then we have 2D, 3D, and 4D as well. For example, X-rays 2D, as I mentioned, MRI and CT scan mostly 3D, and 4D comes especially like in ultrasound. Imagine that you are taking a 3D ultrasound with the kind of video. That means you have x-axis, y-axis, and z-axis, that is 3D, and then you have time axis as well. So it becomes a 4D. And natural images are mainly, how do you say, stored in JPG, PNG, TIFF format. But medical images, we have what we call DCM, Nifty, MHA, or RAW format as well. Apart from that, in medical imaging, we have what we call DICOM format. That is what we call digital imaging and communications in medicine. So it is a standard for communication, like managing and storing medical images. And what in that format, we have what we call metadata. So basically, medical images is like raw image, and within the header, that means metadata. It consists with like resolution, patient position, pixel spacing, slide thickness, what is the machine that we use, and who is the operator, like that. So there are some specific software tools that you can load the image into the tool, and you can read the metadata like this. So I'm not sure this is clear to you. I just took a screenshot. So that is basically metadata to you. So it is sometimes really helpful if you are, when machine learning model take in some another prediction, it would be useful to identify what went wrong, those metadata. If you are a medical student, you might know these like planes and orientations. Like there are image plane like coaxial or transverse, then sagittal and coronal plane. So it is basically separating your body into two parts. Apart from that, we have patient orientation like anterior, posterior, superior, inferior, left and right. So these kind of things, if you are doing machine learning in healthcare, you should be familiarized with, because in metadata, you have those patient orientation as well. So sometimes it's really helpful to identify how patient was in, what is his position, like that, to diagnose some of the cases. Uh, Apart from that, how to measure image quality in especially in medical images. What we have resolution, it is basically pixel per inch. Then we have peak SNR, mean squared error. Then I would like to take some time to explain what we call SSIM, structural similarity index. So basically it combines local image structure like contrast, luminance, and in this metric that structures are patterns of pixel intensities. And apart from that, also, because the human visual system is also good at perceiving structure, and this SSIM quality metrics agree more closely with the subjective quality score. So mostly people are using that as well. And if you do want more details, if you are using Python, this is a GitHub link. And if you're using MATLAB, this is another link that you can check on that, how people are using those metrics to evaluate. Okay, then I will briefly explain how medical images are used in hospital. So if you're a doctor in medicine or nurse, if you're a medical college or nurse, you might know that. So basically, let's say case one, patient, all male patient with history of smoking came to the hospital, and maybe doctor suspect lung cancer and order CT scan to confirm, and doctor confirm the diagnosis, and basically treatment follows. I'm not saying this CT is the exact same thing that may by some other tools or maybe other tests that we are be using. Basically, this will be the steps. Then another patient arrives with numb right hand and cannot recall events in the past few hours. Maybe doctor suspects a stroke or the head CT and confirm the diagnosis and treatment follows. So this is what happened in basically in a hospital. So apart from that, that is the basic step that we see, but there are many steps that need to undergo to take a medical image. So mainly overview, first one is acquisition, obtaining the image, and there are some research, as I mentioned, time taken for those image acquisition can be improved use machine learning algorithm. There are a lot of research, especially for MRI, how to take a good quality image with less time. There are some deep learning methods that is been developing, especially in USA, to take good quality images within less time. Then we have what we call pre-processing. So basically, we are taking complex raw data and generate the image. Then we have what we call image-based tasks. That where machine learning can help. First one is detection. Basically, detection is a certain detecting certain disease markers like nodules, like in cancer. Sometimes doctors or radiologists can miss those details because if these are tiny details, and if we have machine learning, good machine learning algorithm, we can support in that decision. Then we come characterization, basically segmenting or contour a region of interest, and diagnosis based on the image, looking at the size of the nodule and stage it. Like basically, for example, if you have bladder stone, basically depending on the size, we can determine, okay, are you going for laser treatment or basically tablet based treatment. Then we have staging or monitoring as well. Staging and monitoring, basically spread of the disease, like by the time. And then we have kind of a report, and based on integrated diagnostics, analyzing with other data set like blood, body temperature, and etc., we doctors will be able to give a proper diagnosis. That is how it's happened. Okay. Now I would ask how doctor confirm those results. This is like ideal case. So let's say uh provide let's say two different doctors will not agree with their each other decision. That's what we call inter-observer variability and inter-observer variability. So inter-observer means two different doctors or radiologists looking at the same image and come to different conclusion. That means basically some might say patient has cancer, other might say not. Then inter-observer variability means same radiologist come to different conclusion in different situation. That is basically happen on based on other information. So I would say uh, that radiologist suspect you have cancer. Then he will ask in some question. Were you smoking in the past? Yes, yes. Based on that, he will be determining. Okay, this patient has cancer. Likewise, so these are the variability that we have to deal with, especially in medical images, because it's not like identify animal image like dog or cat in image. These really critical cases and consequences are really high. And so if you are using machine learning, you have to think about few things. First one is data loading. So you can treat your data as a 3D or 2D slices, like 3D as 2D slices. So you have different 2D slices or P or 3D analysis. In the meantime, you have to identify, okay, what would be the processing time as well. Then we have image processing, like removing the noises, artifacts, removing noises, and improve image quality. And some of the novel techniques that you are using, that researchers are using, called image registration. So basically, it is the process of aligning two or more images to get the better results. For example, let's say MRI and CT. If you have the patient results for both modalities like MRI and CT, if you can fuse them together and give a better understanding about the disease spread or something like that, That is what we are calling image registration. There are a lot of research this going on this area, basically cross-modality understanding. Uh, then I would also need to give another thing, another remarks about that one. So if you are using medical images, you need to careful about image processing, because we are normally use, if you machine learning, if you've done machine learning previously, we are doing what we call image augmentation. That is basically flipping image, zooming image, like that. So when you are doing those kind of thing, you have to be careful, because first thing, when you are flipping the image, it might not be the same as like we are doing the normal image. For example, if you flip a horizontal flip the dog image, this is still a dog. But if you flip an image like this, that is what we call that you normally heart is in the left side. So if you flip it, it will be another condition called situs inversus. So you have to be careful in that cases. And so if you are doing this kind of thing, that model will be identified this as a model shortcut. So if a patient come up, let's say, uh, when you are flipping it, there might be some additional information going on, and model will be looking into that heart instead of your cancer area or lung areas, and then it will make prediction based on that. So we need to avoid that. So you have to be very careful doing those image preprocessing tasks to identify, to think about it, how to do those preprocessing. Then, yeah, I would explain another thing. So this is the that this is a research that was done by Andrew Ng. You may know about his, that is famous for his machine learning course in Coursera. So this paper was originally published in 2017. So Andrew is one of the most recognized research in the world, and this paper shows excellent result. That means it outperformed the even radiologists as well. So model is better than 4 radiologists combined. So but there are big problem with results. So let me show you. So if you machine learning thing, if you know machine learning bit about it, so here he mentioned we randomly split the entire data set into 80% training and 20% validation. So in machine learning, we have training and test data or validation data. So we are basically splitting our data into that. Then if you look at the number of images, so nearly 112,000 and 30,000 patients. That means one patient has different X-ray images. So when you are randomly splitting into this way, like 80% to 20%, some of your patients will be end up in both training set or both in validation set, both training set and validation set, sorry. And if you split data set randomly, this creates what we call a leaky validation strategy. For example, imagine a patient with a scar in your hand with the previous surgery. So the model might use that information to make prediction. So if the same patient come up with another diagnose, another situation, and model will be used that scar to take a prediction. So every image show with the same scar would belong to the same class. So we call this leaks. And after that, they uh, publish again, saying there are no patients overlap between the sets. So as you can see, even the genius like Andrew Ng is a genius in my machine learning area, but he also mistake that one. So you have to be really careful in that one. Even in these results, they outperform the radiologist, and machine learning model was really better compared to the radiologist. So as I mentioned, uh, every machine learning models need data. So, but in medical data, really expensive. I will explain later why that is. So research came up different solution how to get the data with low cost. So then we have what we call transfer learning. Basically, we train a model in large data set like ImageNet. Then we use those pre-trained data pre-trained weights to fine-tune a medical data set. There are many papers on this. I would list them called Med 3D. Then we have called transfusion. So basically, it is taking X-ray images as X-ray images. Then we have what we call semi-supervised learning. It is among the areas that I have high research interest called semi-supervised learning, apart from the self-supervised learning. So in semi-supervised learning, main idea is you use limited data to train a model, where we call it as a teacher model, and use that teacher model to generate pseudo labels by passing unlabeled data. There are a lot of research in this area as well, both in 2D and 3D medical images using semi-supervised learning. But I haven't seen much of publications lately, but it is a really ongoing field. If you are interested, you can look into that as well. Then we have what we call weak supervised learning. This has become kind of also big business organization called Page.ai, where it has image labels they are able to use to train segmentation of histology images. So it has quite loud form. It is value more, that company values more than 500 million US dollars. So this is another research area that has been people working on. Then we have self-supervised learning. There are a lot of research in this area. So we are using what we call pretext tasks or contrastive learning. So basically we train one task, then we use that knowledge to train on our downstream tasks. So basically we use unlabeled data to obtain useful representation that can help with downstream learning. Then again transfer that knowledge into actual tasks that we need. Then other thing called federated learning, because this come mainly in privacy preservation, because most of the healthcare data set patient don't want to share their data set, their details, for example their age, name, even share with us. So because it contains sensitive and private information, for example, let's say you are a researcher, yeah, do you want data from clinic in USA, clinic in Germany, clinic in Sri Lanka, so you want to build a model. So one thing, you can try to convince them to give you data, put into a hard drive, then come to your location and maintain model. But other way, build a infrastructure in the facilities itself and the data nodes and train a model in each node and aggregate gradient in central server. So basically it's a distributed system. So only information is passed is weights and gradients, that numerical details. So you won't be able to access the patient's private details. Then I will briefly explain current research in machine learning. First one is drug discovery. There is a huge demand in this area because it is multi-billion-dollar industry, and even 90% of the research is drug discovery is failing in the clinical trial phase. So a lot of money invested, but few less results. So that people are trying to integrate machine learning in that area, because try to reduce time and money, because time means money. So some people, this research has developed a system to grow blood vessels, whether the drug changes the outcome, and using machine learning models to whether the number of cancer cells has reduced or not. Then this is kind of a block diagram that I extracted. So as you can see, you have drug discovery, chemistry, biology, and material science as well. So there are some interesting research that going on, especially apply machine learning in like DNA-based data set. How do I identify cancer markers early as possible, like that. So there are a lot of research in that area. This is another research that I was really interested in. This norm collars breast arterial calcification. So X-rays of the breast to find the breast cancer. Then you train the network to predict whether there is a cancer or not. That is basically what people were doing like a few years. And but here they are trying to predict the calcification level. So actually, it is not a deep learning problem. It is basically a, I would say, regression problem, where they try to predict the calcification of the blood vessels. So high level of calcification is potentially sign of the heart disease. So let's say patient come to with the take a mammogram, and as a byproduct, we are able to do a breast cancer scanning as well. So we could detect if you have so mammogram is for breast cancer, sorry, and we could detect if you have heart calcification, and we can warn the patient about it because it can out saying that you have sign of heart disease. Go check, kind of warning signals. So based on the calcification level, so we can say the patients, you have signs of heart disease. Please take a look at it. That is actually quite interesting results that we found. And other thing is this one we call polyp detection. So if you are doctor, you may familiar with colonoscopy, or if you've seen it, where doctors go into the colon and take videos of the colon, and they are looking for polyps that we call as these green boxes, which where the colon cancer can develop. So so typically during colonoscopy, doctor will remove those polyps. But problem is the area of those colon, because it's roughly, it's really large, maybe like a tennis court, but colonoscopy is 5 minutes. So doctors can miss those things usually. So they are in this research, they train images and use on videos, and this has been deployed in USA. So they were having really good results in this one. As I mentioned, uh, they were able to take 95.6% accuracy. They deployed in 2019. The research was in 2018. So they were able to take a high accuracy results. It has been deployed. And one thing that I want to mention, so as mentioned, uh, I would explain it later. Yeah. Yeah. So this is another thing that I want to mention. Then apart from our cases, we are trying to identify canines, basically dogs, valley fever in canines. So basically this comes for veterinary medicine. So basically it happens because of the occurs in wide range of his species like humans, domestic and exotic mammals. Basically inhalation is the most common route. So they develop a machine learning model to identify those areas, kind of a heat map. Then apart from that, as I mentioned, we some research are trying to use electronic health records to prediction outcome after surgery, and they were able to like hospital mortality. So they were able to predict patient mortality based on the data. Now I will give brief guides to how to use AI in healthcare. So if you have project idea, first thing is think about, for example, I would explain this with some example. Let's say you think about a problem. For example, blood glucose measurement. Then you identify what are the existing problem. For example, in blood glucose measurement, what normally you are using, we have a device and we pinch in your finger and take a blood sample, and based on that we are measuring glucose. So what is the problem? Some people don't like it because we are pinching. And so you are trying to develop a non-invasive method to take a blood glucose measurement. Then you will go into internet and try to identify if there are any existing methods for non-invasive blood glucose measurement. If not, you will try to identify some research papers and try to identify how you can measure blood glucose without pinching, without taking blood sample. So then you can try to identify, okay, there are some these techniques, and you build a device to take those readings. And based on that, you decide whether I'm going to machine learning models or other approach as well. Don't think about going to machine learning in first step, because some people are doing that. This is not the best approach. Use the machine learning when it is necessary, not the other way around. Don't try to fit your all problems into machine learning, because it is not going to work. That's I would say. So as I mentioned, you can get data from the device that you built, and let's say, okay, now you're trying to machine learning models. You can do that way. Another way is like find some existing data, because you need data sets to train a machine learning model. So there are these are the few things that I want to mention where you can get data. First one is Kaggle, and then core Mikai challenges, and Grand Challenges, FissioNet, Fast MRI, UK Biobank, and Human Phenotype Project. That is the dataset name. And if you need, you can go to this website and take a look at it. So in this everything, you can find a lot of medical data, especially the UK Biobank is a large scale biomedical data set, basically research purposes, containing a 500,000 UK participant. And this database regularly augmented with additional data. You can find ECG, MRI, like that. So if you are trying to develop a thing or machine learning models for X-rays or something, just go and look in those data set. You will be able to find a good data set with lot of good code base as well. Apart from that, some points that I want to mention. Make sure that patients are not overlapping the training and validation and test set that I want to mention, that I mentioned before. Okay, then I would explain to try to identify biases in the data set. I will explain it a bit later. And if you are trying to use machine learning in healthcare, I would suggest go with PyTorch if you're into programming, and Mona frameworks are great tools. First, try to create a simple baseline and then identify what went wrong. And based on that, try to develop on that. And try to find some latest research in that area. You can find Google Colab or Kaggle for GPU trainings. Apart from images, so basically I mentioned image dataset, but you can use notes from doctors called what we call electronic health records. Also ECG, I'm sorry, I used the same thing twice. ECG measurements, and also like those EEG measurements like that, to take readings, and based on that you can develop machine learning models to identify some abnormalities like that. Apart from that, you can try some wearable device, maybe Apple Watch, Fitbit, those data to, there are a lot of research in that area to identify some of your health problems though using those wearable device. That's what I want to suggest. And I will so I will really encourage you, first create a simple baseline, and based on that try to identify what are the problems, and based on that try to improve it. For I would give example, if you remember polyp detection, this research. So in this one, when they try to deploy the model, they identify some of the images that they are wrongly predicting the class as the polyp. Main thing is that in colonoscopy you have kind of a twist kind of handle, and when doctor is moving, and when doctor is moving that twist, the model was able to identify that twist to as the polyp, because using that twist to as a shortcut. So try to identify those things in your model, and based on that you can develop a really good model, then try to present it, I would say, or maybe you can publish a paper. Okay, other thing, some of the issues that I want to mention in, especially in healthcare data set. First one is bias in data. I would give an example. So there's this research that they develop a model using X-ray images in your chest area. Then they tried to give a, I can't remember what is they are trying to do, but at the end, model was able to predict race of the human, basically saying whether person is black or white. There was no detail in this the training set, only only the images, but at the end they were able to predict the race. When we dig into the data set, they identify. So this was done in USA, and some TB vaccines that were mainly given to the white people, and most of the black people don't have. So model was able to use that as a shortcut, and based on that model able to predict the race of the person as a black person or white person, just using X-ray images, nothing else. So that's what we call biases in data. So try to identify those bias if there's any. It's a huge problem in medical data set as well. And there are some ethical issues and privacy issues. Also fear among medical practitioners, because they are thinking that we machine learning models will try to replace their profession, but I would say we are machine learning models will not replace those things. They basically trying to help those medical practitioners to give better results with a quick time, with a quick getting quick results, I would say. And another thing is high cost of labeling. As I mentioned previously, you cannot label a tumor like using normal persons. I would say normal person or not experts in the area. You can label like dog or cat images, but not tumors, that sort of area. You need experts, at least doctors. But normally when we are labeling, we need like 3 or 5 doctors, and they are labeling it as like this is a tumor, this is not tumor, and then based on that we are taking the majority vote, then we are labeling as a tumor or not. So doctors, we have to spend a lot of money to doctors to labeling tasks, because that is the one of the tedious tasks that we have, and it is very really expensive. So that is what basically I want to mention how to use AI in healthcare. So if you are trying to do a brainstorm project in this side of using machine learning, first try to not to use machine learning, then think how to use like simple algorithms, so some simple approach to develop that task, and based on that try to develop that one. If it doesn't work, then go to machine learning. Your first approach shouldn't be machine learning. Try some simple approach, then based on that decide whether you want to go to machine learning, and then build a simple model. Then based on that you can deploy it or try to identify it what are the areas.